We've talked a lot about how energy can change from one form into another, but we've also talked about the fact that when energy changes from one form to another, sometimes the energy might get lost. And it doesn't mean the energy completely disappears. It means it might get transformed into something that is an energy that we don't actually want. So it might be something like thermal energy that we weren't actually looking for and is really hard to get back afterwards as well. So for an example, if we talk about the electrical energy that's being delivered to an incandescent light bulb, we could ask how much of that energy that we pump into the light bulb is actually converted directly into light energy. And you may be a little bit shocked to hear this, but it's actually only about 5%. So we pump in a whole bunch of electrical energy, but a whole bunch of it gets lost along the way and does not actually get changed over into light energy, which was our goal. Now, it didn't actually get lost, but it turns out that other 95% was just converted into heat, something we weren't actually looking for in the first place. And we call it waste energy because it wasn't what we were looking for, and it's really hard for us to get it back. We've wasted that energy. What we're talking about here is the efficiency of the light bulb. Efficiency is a measure of how good things are at changing energy over from one form to another without losing it to some other form that we're not seeking in the first place. If we actually want to calculate efficiency, it leads us to a fairly simple formula. Now we use a bit of a fancy Greek letter to represent it. This Greek letter here is called eta, but it really just looks like a scripty N with an extra little tail. So if you draw a handwriting N and give it an extra little tail, that's essentially what the Greek letter eta is supposed to look like. But then what we're doing is taking some energy that we get out of it. So in this case, in our incandescent light bulb situation, that would be like the actual light energy that we're looking to get out of it. And we're just dividing that by the energy that we're pumping into the device in the first place. In this case of the incandescent light bulb, that would be the electrical energy that's being pumped in. Now we could just divide those out and get a decimal number, and that decimal number in a sense represents the efficiency, but we typically like to also multiply by 100% so that it puts that decimal into a percentage form. Now, energy, of course, typically we're going to measure in joules. And we're taking energy out, which is in joules, and dividing by energy in, which is also in joules. So if we do a little bit of unit analysis, we can see that, well, we're going to take something in joules and divide it by something in joules as well, and then multiply by something that's in percentage form. Well, when we do that, of course, our units of energy cancel each other out. Dividing joules by joules just gets rid of joules completely. And so our final result will be something that is just in a percentage form. And so in general, joules are what we use for energy, but remember, joules aren't the only way we can measure energy. We could talk about kilojoules or megajoules or even kilowatt hours. Those are all ways of measuring energy. And as long as the units on the top value are the same as the units that we're dividing by, those energy units will cancel out and give us only a percentage. But now this formula gives us the opportunity to figure out the efficiency of some common everyday things that convert energy. So for example, a compact car, well, it takes in gasoline energy. And each liter of gasoline is able to give us about 34.83 megajoules. Megajoules just means a million joules. So this fancy unit MJ just stands for a million joules. So that's just under 35 million joules for each liter of gasoline. That's how much available energy there is when gasoline is pumped into a car. But not all of that energy that's pumped in gets converted into the actual kinetic energy of the car traveling down the road. In fact, only about 6.27 million joules or megajoules of energy is actually being used as kinetic energy by the car to drive down the highway. So we can look at what the efficiency of the car would be. The key with these questions is figuring out the difference between energy out and energy in. Well, we said that the gasoline was what was being pumped in, and that gives us our available energy to start with. So it's the gasoline energy that would be our E in. So I'm actually going to fill that one in first, the 34.83. And I'll leave it for now as megajoules. Remember, if I wanted to, I could convert that to joules, but I'm going to leave it as megajoules for now and show you why in this case that's actually okay. That means the energy that we get out is the 6.27 megajoules, which again is in the form of kinetic energy. It's actually moving the car forwards. What we're trying to find is efficiency, so that's that fancy Greek letter, eta. So our formula says that eta is just taking energy out, dividing by the energy that we put in, and multiplying by 100%. So we can plug in the things that we know. So the energy we got out was the 6.27, and I'll leave the units in so you can see what happens with those. 6.27 megajoules. And then we have 34.83 megajoules that we're dividing by. And then we're going to multiply by 100%. When you divide the megajoules parts, well, we're taking megajoules and dividing by something that's also in megajoules. So even though one of them is in megajoules, as long as the other one is also in megajoules, those two units will cancel one another out. When you divide the number parts, 6.27 over 34.83, you'll get a decimal number that's about 0.18. When we then multiply that by 100%, we get approximately 18% efficiency, which is just a way of saying that only about 18% of the energy that is pumped into the car is actually converted directly into what we were trying to use the car for, specifically getting kinetic energy in this case. So that means the other 82% is just going to waste energy. It's not actually being used for what we want to get out of the car. In some situations, though, we may not actually know a lot of information about the energy itself, but we may know some more information about the powers involved. So we can actually calculate efficiency also based on power using a very similar formula. If we know how much power we're getting out of a device, and we know how much power is being pumped into that device, if we divide those values and still multiply by 100%, we'll get our efficiency value. Once again, we can also just show a little unit analysis that as long as power, for example, was in watts, then we divide by power, which we'll say is also in watts, and then multiply by something that has a percentage. Well, once again, the watt units will cancel out. And in fact, even if we use kilowatts or some other power unit that wasn't watts, as long as we use the same power unit on the top and bottom of that fraction, the units will cancel out and leave us with just the percentage value. So our final unit should just be in a percentage form, even though we're doing this with power in this case. And now we'll just try one last example. So if I've got a 60-watt light bulb, and I know it has an efficiency of 5%, because it's an incandescent light bulb, just like we talked about at the beginning of this lesson, we want to know its power output. How many watts of light are actually being produced in this case? So let's state what we know. In this case, the power that we're putting into the light bulb is actually the 60 watts. So when you see a light bulb with a rating on it that says 60 watts, that means that's how much power needs to be provided to it from the electrical outlet. That's the electrical energy being pumped in. We also know eta in this case is 5%. And in this case, we're trying to find P out. Well, in general, eta is just P out divided by the power that we put in, multiplied by 100%. Before I actually do too much work on this, though, it might be easier if I just plug some things in that I know. So eta is actually 5.0%, and that's equal to P out. That'll be the variable I'm still trying to solve for, but that's divided by 60 watts, and then multiplied by 100%. It's best if we try and get rid of that 100% part first. So if it's multiplied on the right side by 100%, I can divide that side by 100%. And I'm allowed to do a trick like that as long as I do the exact same thing on the other side and divide the left by 100% as well. So when I do that, I get just 0.05 on the left with no unit attached at all, and I get just the P out divided by 60 watts on the other side. I've run out of room at the bottom, so I'm just going to continue my solution off to the side here. Now I can finish it off by just multiplying both sides by 60 watts. So 0.05 multiplied by 60 watts is going to tell us what our power output should be. When we do that, first of all, notice on the left side, when I multiply just a decimal number by something in watts, my answer will also be in watts. When we do that, we get about 3.0 watts, so that is my power output. So if we put 60 watts of power into an incandescent light bulb that only has a 5% efficiency, we are actually only getting about 3 watts or 3 joules each second of light produced. That's what this is really telling us. Of course, you'd still want to follow up with a final therefore statement to summarize all of this information.